Really excited to introduce John Finn as our first speaker. John is a pioneer in the space. He's worked across the deliveries, worked across the payloads, so many different modalities, and I'm excited to hear what John has to say for us today.
Great, thank you very much, Eric. One thing just at the start, I think some of you probably already know this, but if you don't, I have a stutter. And what that can mean is that it can take me a little bit longer to say what I want to say sometimes. Hopefully 10 minutes. I know it'll be tight, but just don't worry. If I'm struggling, everything's fine. It runs in my family. One day we will be editing for that, and I think we'll need capses from people in this room to help us with that. Okay, essentially, one of the problems I think the field has is there's too many mutations. Right? If we think about 7,000 broken genes out there, and on average, each gene is broken at least 100 different times, if not 1,000 different times. Essentially, if we're just going to be fixing individual mutations, we're essentially taking rare diseases and turning them into rarer diseases. And so I just don't think this is feasible because ultimately we would need almost 1 million separate drugs. And so this leads to this idea of programmable gene insertion. This is something I've been working on for almost 10 years now in all different forms, but it's a very simple concept. If a patient has a broken gene, let's give them a functional copy of the gene and put it in the right location, right? Now we can finally harness these endogenous promoters that are much larger and stronger than anything we can squeeze into a vector. Two, it maintains endogenous regulation. And this might not be important for every single gene, but if you think about it, 10 times more of our genome is dedicated to regulating proteins than coding for proteins. So I just think if you can put the gene in the right place, you don't have to worry about hitting the wrong cell type, too much expression, or too little expression. Importantly also, this will be mutation agnostic. It shouldn't matter what actual mutation the patient has. And these are therapies that will grow with the patient. And so ultimately we want to be able to actually treat kids where they'll never even know they were sick in the first place because we put a healthy copy of the right gene in the right location. Now, this is not a new concept. This is what I was doing with my previous company, Tone Biosciences. This is also what Prime Medicine's working on. But I would also argue that this is still a challenge. The technologies available right now, they work, but they're very complicated. We needed a Cas, an RT, we need 2 guide RNAs, we need a recombinase, all this packaged in 2 LNPs and an AAV. But it worked. Actually, this is just one slide from Tome. And after 3 years and a lot of money, we were able to optimize this and actually get this working in non-human primates. I think the most remarkable thing, though, is in this whole journey, the thing I learned is that these recombinases that we were using were never the hard part. The hard part was always optimizing the prime editing step to get that integrase landing site written. One of the things we heard from investors is that even though we did this and it worked, it was too complicated, it was going to be too expensive, and they weren't wrong. We were building one of the most complicated drugs ever. And so, but one of the things I learned is that these enzymes, Large serine recombinases are one of the most efficient editing tools I've ever worked with. They're very, very small. They are one protein that does all the work, and also they're the only editing protein that actually does the edit. Every other editing system, right, nuclease, base editing, or prime editing, all they do basically is damage DNA, and then you hope that it actually makes the edit that you want, right? This is why this might work in an actively dividing cell, but not a non-dividing cell. This might work in a primate, not a mouse, et cetera, because each of those cells has a different repair mechanism. This is not true for the LSRs. If you put them in a test tube all by themselves with 2 pieces of DNA, it will drive that reaction to 100%. Also, they don't write the DNA. They don't care how big the DNA is. And so we've already shown we can do this with 1,000 bases. We can show it with 30,000 bases. It just doesn't care. So again, nature's already solved this problem. It already knows how to put large pieces of DNA in very specific locations. The problem is that it's never done it for any of the sites we care about. And that's really what we're working on right now. So what if we could design recombinases to hit the sites we care about, not the sites that nature solved for? And so essentially, if this is something we'll do, there's a few things we need. Essentially, we need data, models, and we need ways to rapidly optimize the proteins. And this leads to what we're doing at Basecamp. So Basecamp, we're not a gene editing company right now. We are really focused on building the largest database of nature. So we have about 20 times more data than the sum of all the public databases combined right now. And one of the things I love about it is that it is full of LSRs. We have millions of examples of these proteins in nature. And so what we've been doing basically is we've been working with NVIDIA to start training AI on all of this data. And actually, we just actually wrapped up one model, which is actually the same scale as GATC25. So that just gives you a scale of the amount of data that we have. And I think importantly, this is actually new here, we are now actually developing models to start understanding how recombinases work. This is something that's important. So now actually we can prompt on a piece of DNA, and when we look at the recombinases it spits out, over 95% of them actually are active. Now, we haven't solved all of the issues yet. We're still actually working on increasing potency, increasing specificity. But I will say, while we've been doing this, while we've been generating data to fine-tune all of these models, we've already identified natural LSRs that have known activity on human DNA. Now, it's not always the best site, right? But this is also real data. This is not a predicted site. This is real data where we actually took real DNA, real proteins, threw them at them, and looked to see where they went. And so we already have natural LSRs we can start to optimize for. And importantly, these models that we're building that are trained on all this data, they're also helping us accelerate the optimization of these enzymes as well. And so with that, what we want basically, is a world where essentially we can prompt on a piece of DNA, and the models will actually design synthetic LSRs that have the right on-target potency and specificity profile that essentially making these cures almost becomes more of a software problem than a hardware problem. You know, essentially, if we can do this, we can start actually designing cures for many diseases, not just one or 10, but hundreds, if not thousands of them. So we haven't done this yet, but this is, you know, what we are working on. And just one plug, I'm hosting a roundtable, which is completely different than everything I just spoke about. But essentially, I've been working in gene therapy for a very long time. And I think a part of why we're in the place we are is we've been trying to fit it into the wrong model. We've been trying to fit it into the pharma model when actually there's already a very good model out there, which is organ transplants. And anyway, this is a teaser. I'll be having, you know, more of a conversation about this, but I think we need to rethink the way that we bring these drugs into patients. That's it. Thank you very much for the time.